we go along, please do ask me any associated questions or any clarification you want on any of the concepts. This is, we can make use of this time to do that as well. Okay, so this question, you're asked to prove that there's an infinite number of prime numbers. This is like, the Lord's Prayer or whatever something. It's just you've got to know how to do this as a undergraduate student. It's so fundamental to know that there's an infinite number of prime numbers and to be able to prove them. Yeah. Then there's questions about the Euler-Tauschen function. Okay, the Euler-Tauschen function is quite important. It's the size of the multiplicative group of numbers modulo something. Because of that, it's got relevance to the cycle lengths that numbers go through when you raise them to powers modulo something. Okay, and that has consequences, especially on the cryptography side. It's one thing to be discussing with John. You got 3 questions here. Question B is just to give a statement of the definition of what it is. Part C, well, part C and D kind of go together. What you see in part D there is the what we were calling the multiplicative formula for 5n. It tells you what 5n is if you know the prime factorization of the input n, which is useful in practical reasons for calculating it for specific n's, but it's also important for theoretical reasons to have an understanding of what a kind of a near prime factorization of the value 5n looks like based on the factorization of n. Now, we're not asked to give the full detailed beginning to end proof of this. We're asked to prove this is one of the major parts of the proof of this in part C, and then to explain kind of what extra stuff you need to talk about on top of this in order to get to this. Okay. Now, so question 2a, this is, it's in the book. We discussed it in class. We discussed it recently as well because we remember we were doing special cases of Dirichlet's theorem that there's an infinite number of prime numbers in any non-composite arithmetic sequence. So this is pretty much bookwork, and I'd be expecting a good rendition of this from everybody. The one piece of guidance to take note of, it says state clearly any results about divisibility that you rely on. Okay? You don't have to prove those results from the ground up, but just clearly point out where you're relying on known facts about divisibility. Okay? So, how this is most commonly presented is this is a proof by contradiction. So we begin by assuming there's a finite number of primes. Okay. Proof by contradiction works by assuming what you're trying to prove is false. For every well-formed statement is either true or false. It's a kind of underlying principle we're working with. Maybe a bit more complicated than that. Sometimes in the foundations of mathematics, you worry about exactly what a well-formed statement is. But anyway, the straightforward view we're taking is every well-formed statement is true or false. We assume it's false, and from that we're going to derive a contradiction. And therefore, the only conclusion could be that the original statement has to be true. So we assume there's only a finite number of primes, and then you list them, P1 to Pn. This is a list of all of them. Okay, so this is all the primes that there are. P1 to Pn, and there's at least, you can list a few, 2, 3, 5 primes certainly exist. So we assume there's a finite number. And then we consider the integer n by this formula. So you multiply them all together, and you add 1. Okay. And the argument proceeds by considering prime factors of n. Okay? So by a theorem from the unit, every integer factorizes into primes. So let Q be a prime divisor of n. Now, we know something a bit stronger. In fact, every integer factorizes uniquely into primes. We don't need the uniqueness here. So I won't bother putting it down. All we know is simply that every integer must factorize into primes. And that followed straight away really from the definition of a prime. The number isn't prime, it's composite. So it's a product of two smaller numbers. And you just, if those are prime, fine. If one of them is composite, in fact, it must be a product. So you just keep, every time you see a composite number, you factorize it, factorize it, factorize it. Eventually you run out of things to factorize, and you've got a product of primes. Okay. So that didn't need anything too sophisticated. It's proving the uniqueness part of the prime factorizations that required a bit more theory. So where we are in this argument now, we know that n must have a prime divisor q, at least one. But by assumption, well, you see, the assumption we put in place is that there's only a finite number of primes, and that's all of them there in that list. So this prime factor q must equal one of those pi's. Some I between 1 and n. And so in fact, my prime divisor of n is one of those. Then you make the crucial observation. So now we know that q divides n and q divides the product p1 and p2. Now, strictly speaking, we're using a property of divisibility here. Well, I guess you can say Q divides the product. That's true from the definition of divisibility, because we already know that this product features Pi as one of the factors in it. So it is clearly, this product can be written as some multiple of Q. So that's by the definition of divisibility. I mean, you wouldn't have to write it in this detail, but just what I'm meaning is, since the product of all the p's is equal to q multiplied by the product for every j not equal to I of the pj's, where I is this specific value here.
Why is it P2 and not P1?
Yeah, that's a good question. Should be Pn.
Not the
Well, the n is equal to Q1 to.
Up here as well. Yeah, you're right. Thanks for spotting that. So, I mean, this product is clearly Q times just all the other factors. Okay. But now these two divisibility statements implies that Q divides 1. Since 1 can be written as a linear combination of these two quantities. Okay. And that's using another property of divisibility, which is the divisibility of linear combinations. If Q divides this number n and this bracket here, it will divide every linear combination of them. So in particular, it divides the difference. So that's by the divisibility of linear combinations. That's the name for that result. And that's where we are. So that gives us our contradiction. Because the only divisors of 1 are +1 and -1, but neither of those are prime. So Q can't be. So that's our contradictory statement. Okay? So this is clearly a contradiction. This is clearly a contradiction as Q is prime. i.e. Q is strictly bigger than 1. It's part of the definition of a prime number. Okay. Now it's good to always kind of round off proof by contradiction. This is bad, you breached a contradiction. What led to the contradiction is, well, there's nothing wrong with our argument except for the very first sentence, where we assume it's undefined. That's where the problem is. That's what causes the contradiction. So that can't be true. There must be an infinite number of problems. So our original assumption itself must be false. So we conclude that there are an infinite number of primes. Is that okay? Some kind of version, some kind of equivalent argument to that. Some people do construct and present the proof slightly differently. Some people that are interested in the philosophy of maths don't try to avoid proofs by contradiction because they find them problematic from a kind of philosophical point of view. But this proof doesn't have to be presented as a proof by contradiction. It can be presented in a much more constructive way. If you want, you could recast essentially the same ideas, but what you recast it is, you recast it as a algorithm for producing primes. And the input into the algorithm is any list of distinct prime numbers, right? Certainly distinct. Any list of prime numbers is the input. And the output is a number Q, which you know must exist because we know everything factorizes into prime. So it's a prime that divides this number n that you've constructed. And this little argument here shows that the Q must be different from the inputs. So you feed in a list of prime numbers and you get a new distinct prime number out. And then you just repeat the process. You add Q to the end of that list, run the algorithm again, a new prime pops out. Add it to the list, run the algorithm again, a new prime pops out. Okay? In principle, there's not, if you have the computing resources available, there's not, that process will, what's going to stop it? It can never end. You'll keep computing new prime numbers. Practically, you'll run out of resources. You're going to be alive so long. You're going to be around so long. There's only probably so much stuff you can get your hands on to build your computer. There are obviously practical limits that you'll run up, but in principle, the idea, there's nothing to stop the idea running and running and running, continually producing new prime numbers. Okay? So that would, it's the same ideas, but just presented in a different way, much more algorithmic kind of way. Okay. So that kind of a version would be acceptable as well. The other proof we saw that there's an infinite number of prime numbers was we proved, which would be a lot harder to do in here, but we also showed this by proving that the prime harmonic series diverges. And that's an interesting result in itself. As a consequence of the fact that the prime harmonic series diverges, as a consequence of that, you get that there must be an infinite number of primes. So if there was only a finite number of primes, this sum of all the reciprocals of the primes would just have some value, just adding up a finite number of fractions. The fact that it diverges indirectly shows there must be an infinite number of terms in this sum. Okay, but I mean, that's a more complicated argument because it's proving something much more strong. Yes, question.
You know, on the coursework, it was asked to do a proof as well.
Yeah.
It was asked to do a proof and then explain why this provides another proof that there's infinite primes. To do that, would you then have to go and prove the basis part again? You know, like the original question. You'd have to prove that and then go. You know,
Well, do you mean could you use that as a basis for answering this question? And
yeah, or would you have to prove the previous part like we did in the coursework?
oh yeah. So like, yeah. I mean, I don't think it would be enough to say, well, we did something in the coursework that proves this. You know, because I'm trying to assess your arguments there. So, if you just said there exist infinite sequences of coprime numbers which are pairwise coprime, therefore there's an infinite number of primes, you're skipping out most of the argument there. So that wouldn't get the 10 marks. If you showed from the ground up that there's an infinite sequence of pairwise coprime integers, and then argued that that implies there's an infinite number of primes, yeah, although that argument needs more input, it also needs the uniqueness of prime factorization to fully prove it. Whereas the one here, Euclid's proof, the advantage of Euclid's proof is simpler. It doesn't require unique prime factorization. No, it doesn't. It just requires that every integer does factors. Another question? Okay. Okay, so that's a good treatment of that. So shall we have a look at the other questions? So the other questions were about Euler's Toshin function. So in part B, you just asked for a definition of it. So you just want to give a precise definition of it. Again, and a nice definition also has an example or two. Okay, so you should work that in. So phi is a function defined on the integers n greater than or equal to 1. And phi of n is defined to be the count, the number of j, such that j is between 1 and n, and the GCD of j and n is 1. You might prefer to do that as the size of the set of j such that 1 less than or equal to j less than n. The GCD of j and n is 1. If you want to avoid writing English, you could write it like that. That amounts to the same thing, but so does that sentence. Either is acceptable or anything equivalent to that. That hits the nail on the head, so to speak. Okay. For example, phi of 15 is 8. Since, so what are the numbers? 1, 2, 4, 7, 8, 11, 13, 14. So right there, 1, 2, 3, 4, 5, 6, 7. Since these are all coprime to 15, the missing numbers are not. Missing elements, multiples of 3 and 5, are clearly not coprime to 15 because they're multiples of 3 or 5, so they've got a non-trivial common divisor with 15. So that would surely secure all 3 marks. Probably, you just give the definition, you get 2 marks as well. But, don't hold back. Demonstrate your understanding of the thing. And a nice medium example like that shows it up well.
Can you give the formula?
Which formula?
The 5n. So, like each prime factorization.
Oh, well, that's dealt with in the subsequent parts of the question.
Right.
So it wouldn't be appropriate to give it here because you're going to be going on to talk about it in the subsequent parts. And there's only 3 marks going to this, so yeah. Okay, any other questions on that? Okay. So parts C and D are guiding you through the proof of this multiplicative formula. So beginning with part C deals with powers of a prime. Prime powers are often called. So P is a prime and A is a positive integer. Proof that the orientation function satisfies this. That phi of P to the A is P to the A minus 1 times T minus 1. So A is a positive integer. We let A be greater than or equal to 1. P a prime. We want to establish this formula. Now, can you remember the basic principle behind this proof? Yeah, it's a direct proof. There's nothing roundabout about it. It's just a head-on direct proof, just working straight off the definition of the function. Well, there's maybe
Not quite direct.
maybe not quite direct. So what we do is we look at the relevant domain. So consider the domain to choose from, which are the integers 1, 2, 3, etc., all the way to P to the A. Now, our definition that we just gave says that the value of phi of P to the A is the number of elements here which are co-prime to P to the A. So it's not quite head-on direct. We take one little sidestep. We don't count the ones that are co-prime. We count the ones that are not co-prime, okay? And so therefore, the ones that are co-prime are the ones that will be left behind, okay? Because we know how many integers are here. How many integers have I written down? P to the A, yeah, P to the A. So we know how many are there. So if we know how many are not co-prime, we can just subtract, and that's how many that are. So instead, we identify the ones that are not co-prime. Not co-prime to P to the A. Now, for any J, GCD of J and P to the A is strictly greater than 1 if and only if. So what's the crucial condition? Exactly. Well, what's another way of saying, another equivalent way of saying that a number J is not co-prime to P to the A? So, yeah, go on. They have a common divisor.
Yeah.
Common divisor. Yeah.
Common factor.
Common factor. Yeah. P divides J. So you look at this. So when is the GCD strictly greater than 1? When there's some non-trivial common divisor. What kind of common divisor could there be between these two numbers? Well, J is standing for the general things. You look at this. This is quite specific. What kind of divisors can that have? Was quite restricted, okay? Because P is special. P is a prime number. The only things that can divide a power of a prime are other powers of prime. Powers of prime that are less than or equal to this exponent, okay? So P divides this, P squared divides this, P cubed divides this, all the way up to P to the A divides it. But no other numbers divide it, p to the 0, which is 1, but we're only considering strictly greater than. So the only numbers that divide this are the same power p to the a or smaller powers. So GCD is strictly greater than 1 if and only if p divides j, and the justification is since p is a prime number. So the only divisors p to the a are other powers of p, other smaller powers of p. P to b, where b is less than or equal to a. Okay, that's good. So now we've got a nice criterion for counting the numbers that are not co-prime to p to the a. J has to divide them. So the multiples of j. So the multiples of j from the list above, from the domain above, are, sorry, the multiples of, not of j, of p. P must divide j, so the relevant j are multiples of p. The multiples of p from the domain, well, the first multiple is p, second multiple is 2p, third multiple is 3p, fourth multiple is 4p. You keep finding multiples of p there until you get to the last one. Now the last multiple of p on this list is p to the a itself. And write that in the same format as a multiple of p, it's p to the a minus 1 times p. P is the first multiple wherever it occurs, 2p is the second multiple, 3p is the third multiple. Those are all the multiples, and the very last one you meet is the very last one itself. How many numbers have I written down there? P to the a minus 1, because they're counted by their coefficient. 1, 2, 3, 4, p to the a minus 1. P to the a minus 1, which is a list of p to the a minus 1 so the co-prime ones are the ones that remain. Okay, after you've deleted all these. So how many remain? It's simply the number that there was minus the number that you've taken away. P to the a minus p to the a minus 1. So the remaining integers are all co-prime. P to the a, and there are p to the a minus p to the a minus 1, and that factorizes into the desired form. There's that many such integers. So 5, so that gives us our conclusion. Hence, 5 p to the a is as required, p to the a minus 1 times p minus 1. Okay, so something equivalent to that. That proof kind of boils down nicely to just some essential ingredients. It's just list all the numbers, count the ones that are not co-prime. You should be able to kind of reconstruct the argument just from those kind of essential summary of it. List all the relevant integers that you're selecting from, identify the ones that are not co-prime, and subtract. that okay? Any clarity I could give on that, or any related questions? Okay. So part D says, describe briefly what extra property of phi is needed to establish the general multiplicative formula for phi, namely prime factorization of n is that, and phi of n is that. So what extra property is needed? Well, it's the property that allows you to combine all the results from part C with the different primes that divide n, combine them all together. Okay, so it's that multiplicative property. Okay. So what I'm going to do is I'm going to say what the property is, but also then indicate how the argument, how the proof goes. So I'm not required to prove the property. It just says describe briefly what extra property of phi is needed. On reflection, there's only 3 marks for this, so I would have given 3 marks if you just identified the correct property. But for us here now, I'll also go through the remainder of the proof then. So the required property is that phi is a multiplicative function. Which means that now multiplicative if you stop a mathematician in the street and ask them what's the multiplicative property, they'll say this. But within number theory, the multiplicative property means this, but only when the A and B are co-prime. I guess we're talking about that we have to define what 5, 0 is.
What did you find it? What do you want it to be?
I think it better be 0, I think. Because otherwise the factorization, this property won't work. But 0 isn't co-prime to anything. It's apart from 1. So it should probably have the value 0 and 1. Wait a minute, just avoid 0. Okay, so that's the multiplicative property in number theory. In general mathematics, the multiplicative would just be referring to this kind of property of a function. But in number theory, in order to call it multiplicative, we only ask that it's true on co-prime factors. If it's true all the time, it's called completely multiplicative. The Euler-Toscher function is not completely multiplicative. We did meet a completely multiplicative function, which was the Legendre symbol. The Legendre symbol on the first argument, modulo prime, that was a completely multiplicative function. However you factorize n, you can factorize the Legendre symbol. Okay, so that will get you the full three marks. But just for our purposes here, we can then argue that this is the prime factorization of n. So in particular, i.e. the pi are distinct primes. And all these alpha i's are strictly bigger than 1, strictly bigger than 0. So that's the prime factorization of n. Then phi then is phi of this. Phi of that product. And it's the multiplicative property that allows you to take your product operator and put it outside. Okay. So that's by the extension of the multiplicative property. By extension, I mean the extension to multi-products instead of just products. Two things, A and B. Just like associativity implies general associativity, or linearity on two summands implies linearity on any number of summands, any finite number of summands. Similarly here, if it's multiplicative on two factors, it's going to be multiplicative on any finite number of factors. But you should note here that it's because that's the reason why I emphasize this point. It's because the PI are distinct. Because the PI are distinct, each different prime power is co-prime to all the other ones. So if I is not equal to j, the GCD pi alpha I and pj alpha j, just like we discussed at the start, the only divisors of a prime power are smaller prime powers, and if pi and pj are distinct, the only common power that there is the power pi to the 0 or pj to the 0, which is 1. So those are co-prime. So therefore we can apply the multiplicative property. And then you just appeal to part C. Each of these 5 values comes from part C. Okay. So that's how we prove the multiplicative formula for 5n. Now, of course, in the unit, we have to do a proof that 5 is multiplicative, which, yeah, again, we proved it fairly directly. Remember, we had this big grid of all the integers from 1 to a times b. We arranged them in a rectangle of width a and height b. And we talked about where the ones that were co-prime to ab were. And they were in various rows and columns, and that allowed us to count them. And we argued that there was this many elements in the whole rectangle that were co-prime to ab. Okay. So any related questions to that? Okay. So that was questions 1 and 2. Question 4 I did first. I did that at the end of last week, didn't I? Question 4. So I think that leaves question 3 is the only remaining one. So let's at least get it started. Okay, shall we? So this is a question all about congruences. Begins, got these questions do, just asking you for a definition. So carefully state the definition of the congruence relation. And then as a follow-up question, how does it relate to remainders left by a and b upon division by n? You divide a by n and you divide b by n. Okay, so first of all, let's get the definition that we had in the notes. So for integers a, b, we say a is congruent b modulo n, written as a congruent to b brackets mod n. We say this to mean that n divides the difference. So that was the definition we get. N divides the difference. So that would suffice as the definition. If a and b are divided by n, to leave minimum remainders R1 and R2, i.e. you write A, say, as Q1 n plus R1, B as Q2 n plus R2, where the remainders are between 0 and strictly less than n. So that's just lays out what it means to divide A and B by n. Well, the linkage, so the question said, how does the congruence relate to these divisors? It says that, well, A and B are congruent if and only if R1 is equal to R2. That's the link. Yeah. So the relationship is between these two concepts is A is congruent to B mod n. That's equivalent to saying that R1 is equal to R2. So they leave the same remainder. Notice that it's important there that we're talking about the minimum remainders. If you're sloppy in your division and you leave a large remainder, which still has some quantities of n, which is bigger than n, then of course it'll look different to R2. The point is, if you kept doing the division until you can't do any more division by n, so you got minimal remainder, strictly less than n, and positive, then R1 will equal R2. Is that okay? So that would hit, something like that would hit the full 3 marks. Notice we're being precise, we're not leaving any, we're trying to make very precise statements all the time. And really hit the nail on the head, okay? Okay, maybe the rest of the question I'll leave to when I see you next, which will be, so next week we'll have a lecture and tutorials next week. Next week's the last week. Okay. So certainly finish off this exam and you can look at some other different type questions as well. Okay, thanks for your attention. I'll see you then.